there is any connection problem in between, you're not able to hear, or there is some disruption, feel free to use the WhatsApp uh, group. You can just ping me, inform me in the group that there is any connection problem and something is not audible. Uh, so many times I'm seeing that the connection is fluctuating. So please make use of the WhatsApp group to inform immediately. All right. So now I guess you are able to see the screen, and I'll go to the OneNote, and the recording is already going on, I guess. Yes. So last time we discussed some basics of inverter operation, and we also looked into the power consumption concept, how the power consumption happens in digital circuits, and how is it different from power consumption of analog circuits. Uh, we discussed several reasons why digital is preferred for computing, why we digitize the raw analog signal as soon as possible after some analog preprocessing into digital signal. So these are the reasons we discussed, and we did some more detailed analysis of the power consumption problem, and why your power consumption in analog circuits can be more, and especially if you are having millions and billions of these gates, you will have even each gate consuming, say, a fraction of milliampere. Multiplied by those millions of gates, it will lead to huge power, which is not practically possible, right? So per chip, we cannot have that much of power. It is not practical. So that's why using analog circuits alone, we cannot do such a large scale computing. Every large scale computing operation is transferred to the digital domain. There are applications, however, where analog domain processing can be done. Applications where very low power sub-threshold circuits of analog domain can work. Those examples we will take a little later. But again, this is not a generic application. In most generic cases, the computation will be transferred to digital domain. In fact, we have also done some work earlier where we have shown that in certain applications, analog domain processing can be advantageous, but those are exceptional cases where sub-threshold analog circuits can work, where the speed requirement is very less and analog mode processing is sufficient. So we will take some examples like that. But general digital circuits will be used for heavy computing. So any question, and I had asked you to go through the inverter chapter of Jan M. Rebe. There is a very I would say basic chapter describing the inverter operation, inverter characteristics, dynamic operation. We have already covered many of those things, like the speed issue. Uh, I think somewhere we had discussed the parasitic capacitors and the speed delay, uh, apart from power consumption also. So if I go back and try to see where is the speed discussed, so yeah, I think it was discussed in the simulation example. So that was not covered in the notes, but it was covered in the simulation example where we had discussed the sizing of the inverter, effect of sizing on rise time, fall time, effect of external capacitor, how to assess the power consumption. So all those things we had discussed in the simulation example. So before we proceed further, any question regarding whatever we have covered? So in the simulation example, remember we started from a single inverter and then we went to two inverters. We looked at the sizing issues, and we tried to see what is the effect of increasing PMOS size or increasing NMOS size. All those things we discussed. So any question before we proceed further related to what was covered in the last session? So I will go to a new page. Meanwhile, new page means okay. So any question before we proceed? So remember that last time we were looking at some basic ideas related to the inverter operation. You may have a CL. We discussed that what are the parasitic capacitances at the output node, at the input node. We discussed that how the power consumption mechanism works, not only from the VDD, but also from the source which is driving the input side. And then when we connect two inverters, what happens? Where is the power going? What is the cause of power dissipation? And also speed issues like the charging, discharging of the capacitor, the waveform, how the rise time for time gets affected. All those things we discuss qualitatively. And in the Rabbe chapter, some of these things will be more quantitative. So they will do the derivation of the rise time, fall time. They will look at the transfer characteristics. Those things I'm trying to speed it up and avoid the quantitative derivation, because the theoretical derivation of that can be seen in those chapters. But the main idea is to give you the intuition that how uh, the sizing will work, how it will affect the key parameters like delay, rise time, fall time, power consumption, the transfer characteristics of the inverter, all those things. So any question before I continue? So one, feel free to interrupt and stop me in case you have any question. So one point that we had, I think, discussed briefly was inverter transfer characteristics. Transfer characteristics. What do we mean by inverter transfer characteristics? So here we take an inverter, apply an input signal going from 0 to VDD. So the input signal will be swept from 0 to VDD, V in, and we want to see how the output signal changes. So it is something like putting a DC source over here, putting a DC source over here, VDC, and ramping this VDC from 0 to VDD in some time t. And for each value of the input, we try to see the output. So how will we plot this? So this is V in axis, this is V out axis. So starting from V in equal to 0, we are going to go to V in equals to VDD, right? So V in is going to be swept from 0 to VDD. And as a result, the V out is going to change. So when V in is 0, we know that inverter will be, output will be equal to VDD. And when V in is VDD, output will be 0. So these 2 points we are aware. In between, there is a transition. So initially, as you are increasing the V in from 0, going on increasing, at what point it will start dropping? At what point it will start dropping? Am I VT of which one transistor?
N, VTN.
N, right? So because initially the output is high because NMOS is off, PMOS is on. Now, till the time input voltage reaches the threshold voltage of the NMOS, the current in the NMOS is very less. And as a result, the downward path is remaining off. But the moment you reach VTN, that means the threshold voltage of the NMOS transistor, you start turning on the NMOS. Now the NMOS is also starting to sink current. And at that time, PMOS is also on because you still have VSG, which is greater than mod VT of the PMOS. So both of them will be conducting, and NMOS is just starting to conduct. Beyond this point, as you make the gate voltage higher and higher, input voltage higher and higher, NMOS current will start increasing further and further, right? As a result, the voltage will start going down. So in this region of the transfer characteristics, both NMOS and PMOS are on. That means in this region, you are having both NMOS, PMOS conducting current. You go on dropping the output voltage because NMOS is becoming stronger. And at a certain point, your input voltage has risen so high that the PMOS is going to completely turn off, right? What will be that point?
VDD minus mod VDD.
This will be like VDD minus mod VTP. So at this point, there is the PMOS is completely, or ideally the PMOS is turning off. Remember that it will have some non-zero leakage current that we will discuss shortly. But ideally, if I ignore leakage current, I can assume that after V in crosses VDD minus mod VTP, the output will be getting clamped to VDD because now the PMOS is completely turned off and NMOS is on, which will be discharging the capacitor completely to ground. Then there is no more fight between NMOS and PMOS. So from the point V in equals VTN till the point V in equals to VDD minus mod VTP, there is a fight between PMOS and NMOS. PMOS and NMOS both are conducting, but after this point, the PMOS has turned off, NMOS is strongly on, and it has discharged the output to ground. So this is the transfer characteristic, voltage transfer characteristics on the inverter, right? And in this region, we can figure out, which transistor is in what state of operation, right? So if I draw a 45-degree line, which means V in equal to V out line, it will cut this curve somewhere, right? And ideally, we would like this curve to cut the V out equal to V in line at VDD by 2. Why so? Because ideally, it will be good to have the inverter switching threshold, inverter trip point, as we call it. What is inverter trip point? This is, I can name it as inverter trip point. This point, I can call it VTINV, whatever. You can name it whatever. But this is the inverter trip point at which the V out becomes equal to V in. So, or that means the input value for which the output is becoming lower than VDD by 2. So now this point, ideally we would like it to be equal to VDD by 2, so that when the input crosses VDD by 2, we can say that the output is going to be close to 0. And when the input is lower than VDD by 2, output is close to VDD. There is something called noise margin that you might have studied in the Rabe chapter. If you have studied the Rabe chapter, what is defined as noise margin in this case? So in this case, which is the high gain region? So as all of you have seen in analog circuits also, there is a region which is having high gain and is depicted by the slope of the curve. So del V out by del V in is high in this entire region, right? So it is highest here, the slope is highest here, and then it gradually dies down here, So the highest gain region, the small signal gain, if we talk about, it is in the middle, right? In the middle, you get maximum dV out by dV in. So if I plot this curve, if I just differentiate and plot, you can easily get the dV out by dV in. It will be peaking somewhere here, right? Peaking somewhere here, and then again, magnitude I'm plotting. So it will again, go down. So this is dV out by dV in. Maximum gain. So we know that in analog circuits, we try to bias the amplifier at the maximum gain point. Whereas in digital circuits, we are operating either here or here. Either, output is VDD or ground. Analog circuit, we are trying to operate at this point, close to the mid value. And now for digital circuits, we have the concept of noise margin. The noise margin, it basically, we know already, at least conceptually, we have discussed that digital circuits have bigger noise margin. So what gives that noise margin? What is responsible for that bigger noise margin in this case? So here, how do we define the noise margin? There are two definitions of noise margin. There is a low to high transition, high to low transition. So if you look
Low
at,
to high transition,
say,
we can say
yes, anybody
0
saying
to
anything?
VTH.
Sorry,
Hello.
yes,
So for
yes,
the
go ahead.
high one, we can say for the high we can say 0 to VTH, and for low it is VDD minus VTP to VDD.
Yes, so basically the value which will cause the output to go in the high gain region, right? So if the initially your input is 0, initially when you're starting, input is 0, and you gradually increase the input signal till VTN, it will not start decreasing significantly. It will remain clamped to VDD. But the moment you cross VTN, the output starts decreasing steeply, and therefore there is a significant change in the output. So roughly the lower noise margin, we can call this as VTN. So effectively, what does that mean? That if you have an inverter, and you are having a logic low level, you can have either logic high or logic low, Vin equal to logic high, logic low. So as long as your input is, suppose input is noisy, suppose the input is noisy, as long as it is below, the magnitude of the input disturbance is below VTN, output will not see significant change. Output will remain close to VDD. It will remain close to VDD. So this will be just the opposite. The moment this noise at the input starts crossing this VTN, suppose the input disturbance becomes larger, starts crossing the VTN, getting deleted automatically. I don't know. Strange. So suppose the input noise starts crossing this VTN, then what will happen? Output side also you will start getting significant disturbance. It will start dropping. It will become more prominently visible at the output. That's why it is termed as the noise margin. Right? All of you are able to follow this? So as long as per these characteristics, as long as the input signal is lower than VTN, the output is still close to its settled at VDD, it is not changing much. But the moment it crosses this VTN value, then you start getting prominent disturbances at the output. And then what will happen? It will amplify further. This signal, if it goes to the next stage inverter, it will further get amplified because this can be a high gain region. As a result, it will amplify the signal. Disturbance may become more and more, and it may corrupt the signal level. So likewise, for the other side, if the signal is close to VDD, input signal is close to VDD, but there is some noise and it goes lower than VDD by this magnitude, VDD minus, this is VDD minus mod VTP minus VDD, right? So this is VDD minus this whole thing. So actually it is just mod VTP drop. So this from here mod VTP. So if this disturbance is lower than mod VTP, then output will remain clean. But the moment this disturbance becomes more than mod VTP, again you will start seeing disturbance at the output. Right? You will start seeing disturbance at the output. That's why we can term this as the noise margin. So in digital circuits, we get significant noise margin. We can tolerate significant amount of supply noise. So in a advanced node, suppose we are talking about 65 nanometer MOSFET. All of you are using which MOSFET model, 65 or 180 in the LT5 simulation?
45. So it had 180 and then it had 45.
65.
Somehow, I think your volume is not very high. So you are using 65. Somebody said 65. I also heard 180.
Sir, basically we are using the 45 nanometer MOSFET model which you have given, and then we are using 65 nanometer in that one.
Okay, so 65 nanometer, I hope you have been able. 45
Yes.
nanometer model, I had asked you guys to put, save it as a text file, and then it should be able to work. So
Yes,
that's
sir.
what you're doing, this 45 one, right?
Yes, sir.
Yes. So 45 nanometer, for example, the supply voltage that you can use is 1 volt or at max say 1.2 volt. Supply voltage is technology dependent that we will discuss when we look at the scaling concept. Uh, so if you look at the 45 nanometer technology, assume that the VDD is say 1.2 volt. For 1.2 volt VDD, we have say VT of these MOSFETs around say zero point 0.4 volt at max. So on the upper and lower side, we get around 0.4 volt, 0 to VDD, 0 to zero point 0.4 volt, and VDD is 1.2 volt. So 1.2 volt minus zero point 0.4 volt, so 0.8 volt. So this much noise margin we are getting on both sides. That means it can tolerate a couple of 100 millivolts of VDD noise easily, right? So that's why we say that in digital circuits, we can handle more VDD noise, supply noise can be significant, but still the circuit will work. So 100, 200, 300 millivolt of supply noise also it is able to handle. But in case of analog circuits, we have already seen that even a little bit of noise is not acceptable because that is directly going to corrupt your analog signals because we are concerned with exact level of the analog signal. This noise margin concept should be conceptually clear to all of you. Any question before we proceed? So don't hesitate in asking. You may think that it is a simple question, but even simple questions related to any concepts can be useful for others also. So whatever doubts, whatever questions, discussions required, you can keep asking. Okay, so the next part, I hope my volume is loud and clear, right? So in case you find any fluctuation, please inform. So the other part that you might have seen is the trip point. So we discussed that the trip point, we are assuming that, okay, it should be ideally close to VDD by 2. But what happens qualitatively to the trip point when we change the sizes? So let us see. So I think there is a
Sir, at trip point voltage, both the MOSFETs will be in saturation, right?
yes. So what is the question?
Sir, I just confirmed.
Yes. Can you complete your question?
If
No,
both
sir,
are
it was not a good.
connected, if both are in saturation, wouldn't it lead to the VDD and ground being connected?
It seems like I'm not able to hear very clearly. So either there is a volume problem. One, can you repeat? Be a little bit louder.
Oh. So
Hello.
at the trip point, since both of these are in saturation, won't
Yes.
the won't the VDD be connected to ground?
Yes. So that's what so definitely in that region VDD is connected. So let us revisit the operation region. So at all these points, we know what is the operation region, and when we are in the high gain region, definitely we have both the MOSFETs on till this point. We already discussed what are these 2 points, VT and mod, sorry, VDD minus mod VT and VTP, whatever. These 2 points. So between these 2 points, we know that NMOS, PMOS are both going to be active. And there is a trip point at which V out is equal to V in, right? This is the trip point, which is the intersection with 45-degree line. And here we have V out equal to V in curve cutting this particular line. So this is the definition of the trip point. This is V out equal to V in. So at what point of input V out is equal to V in? So region of operation point of view, if I look at this region, the region 1, I call it region 1, and you can call this, say, this point as region 2. You can call this region 3. So in region 1, what is happening? That is easy to see, right? So region 1, your PMOS input is close to 0. PMOS is in what state? what state of operation PMOS is in the region 1? Yes, anybody
Triode.
quickly?
Triode.
Deep triode, right? So why it is deep triode? Because
Because sir, it's below VTN, so the capacitor is just it has not fully discharged yet. So sir, the
forget
saturation
about
condition is
capacitor.
not
I
met.
need to talk about the MOSFET's conditions. MOSFET condition depends upon the terminal voltage. So in the region 1, why PMOS is in deep triode? Because the VSG is greater than mod VTP, first of all, right? Because input voltage is 0 or much lower. As a result, VSG of the PMOS, in this case, VSG of the PMOS, this things I can delete. So VSG of is greater than mod VTP, and VSD is close to 0 because close to the origin, it is very small, or close to 0, right? VSD is close to 0. So definitely this is the condition for deep triode operation for the PMOS. Is that clear? NMOS, anyway, we know that it is cut off, right? Because NMOS, the gate voltage is lower than VTM, so this is cut off in region 1. What about region 2? Region 2, things are changing. The input voltage is increasing from VTN going all the way to VDD minus mod VTP. So in the first half, if you look at this, what is the, when the NMOS is just turning on, what is the state of NMOS?
Saturation.
For NMOS in this region, so VGS
Saturation.
just after VTN, VGS is greater than VTN. So definitely it is turning on, but the drain voltage is much higher. It is close to VDD, right? So VDS is greater than VGS minus VT, or in other words, you can say, because this is close to VDD, closer to VDD, gate voltage is just higher than VTN. So you can just plug in some numbers also. So VDD means 1.2 volt or 1 volt, and you are just increasing the gate voltage further. So maybe 0.4 volt, right? Something like that. So in this region, the VDS is around 1 volt, 1.2 volt, VGS is 4 volt. And for saturation region operation, we just need VD of NMOS to be greater than VG minus VT, right? So S is common, so I can just say if VD is greater than VG minus VT, it will be in saturation. So if in this region, gate voltage is lower, drain voltage is higher, definitely it is going to be in saturation. So in the second region, I can divide it again in multiple segments. I can divide it into say 3 segments. So I can further divide it. Again, I don't want to go into detail. I was hoping that this thing you have read in the Razavi, the Rabbit chapter. So region A, region B, region C. So in region A, 2A, 2A. Conceptually, we can just look at. So 2A, we have NMOS in saturation. What about PMOS? In 2A, what is happening to PMOS? 2A means this region, right? So this region.
Triode. Normal triode.
So still early on, if you look at the gate voltages, for the PMOS, in this region, the gate voltage is still low. This is 1.2, VSG is large, and VDS is still large, right? It is say 1 volt. So VSD for the PMOS, if you look at this condition, the VSD is very small, VSG is large. So for PMOS, what is the condition? Same thing. Only thing is the VDS becomes VSD, VGS becomes VSG. So in this case, the gate to source voltage is large, where gate to drain voltage is small. So for the PMOS, what is the condition? This is for NMOS. For saturation region, this is the condition. For PMOS, VSG minus or VSG, if it is greater than VGS, VDS is greater than VSG minus mod VTP. So in this case, I can say that VSD is, as long as this is greater than VSG, minus mod VTP. Now again, the drain, in this case, the source part is same. In both the cases, the source part I can cancel out. So it will become, so remember, how do we remember the condition for NMOS, PMOS? So the pinch off concept, right? So that you can recall so that there is no confusion. So for an NMOS, the pinch off occurs when you have the channel region getting clipped at the drain side, right? So remember that, this is the, suppose, so this is the drain region, you have a gate voltage over here, and you are having source potential on the other side. So if I assume that source potential is 0, then the channel at this point will get clipped if the gate minus drain voltage is less than VT, right? Because we need a channel to be formed. If the channel is to be formed, VG minus VD should be greater than VT, assuming that source voltage is 0. Source is a common in both the sides. So in order for the channel to be formed here, I need VG minus VD should be greater than VT of the NMOS, because then only, assuming that whatever VD you are applying, this is N plus, the same voltage will appear here almost at this point, and the gate voltage is here. So between the gate and the channel, on the drain side, between the gate and the channel, the voltage is VG minus VD, because the gate is VG, drain side, it is VD. So drain contact, the channel potential is close to VD. Therefore, if VG minus VD is greater than VT, then the channel is on. At that time, channel is formed. But the saturation region condition will be when the channel is pinched off. That means VG minus VD is less than the VT. That means the drain VG gate voltage minus drain voltage is less than VT. There is no channel formed at this point. Channel is pinched off. That is the condition for NMOS. Likewise, you can derive the condition for PMOS, right? So for PMOS, also remember, whenever there is a confusion, again, for PMOS, same thing. You have the pinch off appearing at the drain region. But what is the condition in the case of PMOS? So for the drain, it is that, suppose, for the PMOS, we are assuming source is at VDD, and drain is some VD, and you are applying some gate voltage VG. So once again, we know that for the PMOS channel to be introduced, at this point, we need the potential between the channel VCH, which is the channel potential at this point at the drain, minus VG of the PMOS, that should be greater than mod VTP, right? So as long as the now V channel at the drain is approximately equal to the drain potential, so VD minus VG should be greater than mod VTP. So for both these cases, you can remember, using the physical phenomena, like how the clipping happens, how the pinch off happens. Based on that, whenever there is a confusion, you can derive that what is the condition for the PMOS and NMOS. So for this NMOS case, again, because the source is common on both sides, we just say VD greater than VG minus VT. And in case of PMOS, this is the condition. So in this region, because the drain to source potential is low and the gate to source potential is high, we are getting in the region A, PMOS still in triode region. Is it clear? Any question on this? Now region B, I'm choosing close to the midpoint, that is in this central region. Central region, assume that you are exactly at the midpoint and their output is, say, close to, say, VDD by 2. So in that region, what is happening? In the central region, what is the condition of PMOS and NMOS? Assume that, you are close to VDD by 2, just put some numbers. I'm not doing, detailed derivations. So here, suppose this is 0.6 volt VDD and the VDD is 1.2 volt. This is 0. Input is also, suppose, close to 0.6 volt, right? So let me draw it afresh. So for the central region, there is a way to scroll down, I guess. Scroll down. In the central region, What is happening? Just for clarity, I'm drawing it afresh. For central region, I'm assuming that this is close to 0.0 VDD by 2. This is assuming that in the VT transfer characteristics, you are getting it close to, now it's not necessary that it will be exactly VDD by 2, but assume that, this point, this is something close to VDD by 2. This is also close to VDD by 2. So this is 0.6, 0.6, 1.2 volt, 0 volt. You are clamping the input close to VDD by 2. Now, in this case, if the VT is say 0.4 volt for the NMOS, VTN, mod VTP is say also 0.4 volt approximately. So what is the condition for NMOS? VGS is
Saturation.
0.4 volt, VDS is 0.6 volt. So still you have VGS greater than VDS, right? The VDS is in fact, assuming in this case it is even higher than VGS. So we know that here VD is greater than VG minus VT. Definitely there is no problem for NMOS. So therefore in the central region, region 2B, the NMOS is in saturation. What about PMOS? So if I assume these voltages, what is the condition for PMOS? Is there a channel formed for the drain side of the PMOS? What is the condition for the channel to be formed for the drain side of the PMOS? Remember, how will you assume that for the channel to be formed at the drain side of PMOS? Condition is that VD, right? Because ultimately the VD should be higher than VG plus mod VTP, right? Because here, unless the drain potential is higher than the gate potential by mod VTP, it will not form the channel, right? So in this case, definitely the drain potential is 0.6 volt, gate potential is also 0.6 volt. So definitely you have the case that VD is greater than VD is less than, or basically we can say that the channel potential at this point is not sufficient to form the channel. Sorry, the drain potential at this point is not sufficient to form the channel because it must be greater than the gate potential by mod VTP. Then only the drain side channel will be formed. So we can easily say that PMOS is also going to be in saturation. Channel not formed at the drain potential means pinch off, right? That you have studied in your basic electronics, analog electronics, digital electronics everywhere. So in this point, the drain voltage is almost equal to the gate voltage at the midpoint. And as a result, there is no channel formed at the drain side and PMOS is pinched off as well. Both are in saturation. So therefore, you have this condition. And both are in saturation means definitely if you bias both NMOS, PMOS at the midpoint, you will get a static current because both are on, both are in saturation, you will get a static current. And because both are in saturation, you have the small signal model applicable. You can apply all your small signal analysis and you can make this work as a amplifier as well, because in the central region, you have bias risk such that V in equal to V out, and it is in the high gain region. Both are in saturation. Small signal model can be applied. It can be made to work as an amplifier, right? So in fact, inverter in this configuration can be used as an amplifier also. So the question is, how do we bias it to operate as an amplifier in this condition? There are many circuits in practical circuits also in some cases inverter in this particular configuration where V is equal to V out can be used as an amplifier because you are in the high gain region. Both PMOS and NMOS are in saturation and small signal model that you derive for PMOS and NMOS are valid because they are used in saturation region, and you get good signal gain from one of these stages. So if you have to use this as an amplifier, definitely we need to bias it like this. V in is equal to V out. We need to enforce this. So I will get to that biasing point. How do we bias it in the amplifier for the amplifier operation? I will revisit that. So just note this point that is at this point, both are on, both PMOS and NMOS are in saturation. Small signal model for saturation region operation is valid, and you can use the inverter as an amplifier in this configuration with this kind of DC condition. I will get back to the actual operation. How do you make it operate as an amplifier? But going further in the region 2C, 2C, when you get close to this point VDD minus mod VTP. So close to this point, what is going to happen? So again, I will just put some numbers, tentative numbers. So in this region, I have divided the central region into three parts: upper region, lower region, mid region. So I'm talking about the C part, A, B, C. C part, assuming that the output is close to VDD minus mod VTP. That means, sorry, the input is close to VDD minus mod VTP. Output is close to ground. Suppose output is close to say 0.1 volt, 0.2 volt, something like that. VDD is 1.2 volt. Input is VDD minus mod VTP. So something like 0.8 volt, 0.9 volt, something like that. So in this case, what is the condition of NMOS? All of us can see. What is the condition of NMOS?
Triode.
Triode, because if I assume that VT is around 0.4 volt, and here we have VG minus VD, gate to drain voltage. If you see, drain voltage is lower than gate voltage by more than VT. If I assume that mod VTN, or sorry, VTN is around 0.4 volt, definitely from the drain to source, sorry, gate to source, gate to drain actually. So from gate to drain, the drop is 0.6 volt. Definitely, therefore, there is a channel formed at the drain side. That is the easy way to remember. So if for channel to be formed, we need gate to drain voltage. The difference should be greater than VT of MOSFET. Then only the channel will be formed. Here it is 0.8 volt minus 0.2 volt. Therefore, it is in triode region. So MOSFET is in triode region because channel is formed at the drain side. What about PMOS? PMOS is the channel formed at the drain side. What do we need for the PMOS channel to be formed at the drain side in this condition? Quickly. What is the, suppose mod VTP is 0.4 volt. So what is the drain voltage required for the PMOS with this gate voltage at 0.8 volt, VG equal to 0.8 volt? What is the drain voltage required for the PMOS to be in triode, or basically to have the channel form at the drain? Triode means the channel is formed at the drain side. Saturation means the channel is pinched off at the drain side. So based on that, what is the drain voltage required for the PMOS for the channel to be formed?
1.2 volt, 0.8
1.2
plus 0.4.
volt, right? So V plus mod VTP, whatever is the gate voltage, the drain voltage should be higher than VG plus mod VTP. But that is not there. This is much lower than that. Definitely PMOS, you don't have a channel form. So PMOS is in saturation. And this is clear to everyone. And then finally, in the region 3, you have PMOS, the PMOS is cut off that we have already seen. And NMOS is for the region, the third region, when the output has become almost close to ground and input is close to VDD. NMOS is further deep in triode region. And now because the gate voltage is so high, it is going higher than 0.8 volt. So the PMOS is going to be cut off because the gate voltage is high, VSG is going to be low. So these are the region of operations. You can understand how the region of operation changes across the transfer characteristics. And what we see is you will get, if you plot the DC current, you will get also maximum DC current in the central region, right? So at the lower side, the NMOS is off. At the higher side, PMOS is off. But in the central region, both are on. And therefore, you are going to get the maximum current around the middle region. So in this circuit, the maximum static power means the direct DC current flowing between VDD and ground will happen between these 3 points, A, B, C, and it will be peaking around the B point. Because as we move away from the B point, the current either in the NMOS is becoming weaker or PMOS is becoming weaker. If you go higher than B, if you are going for input voltage higher than the B point, the NMOS current is becoming stronger, but PMOS is becoming weaker. And if you go for lower than B point, what we can assume is that the NMOS current is becoming weaker. But eventually, the current in both of them is going to be same because they are in series. And therefore, if you look at the overall current, it will depend upon the on condition of PMOS and NMOS both. So the maximum on current between VDD and ground, the direct DC current or the static current between VDD and ground will come when both of them are maximally on together. And that is optimal point where both are in saturation. So around the B point, you will get the peak current close to the maximum current also. So this, this point conceptually should be clear that, okay, across the entire transfer characteristics, as we move from V equal to 0 all the way to V equal to, VDD, how the MOSFET's operation region change. And if we are looking at the point B for analog operation, we can make it work as an amplifier. But in digital operations, we operate them in the region 1 or 3, region 1 or 3. Either PMOS fully on or NMOS fully on, and vice versa. Any question before we proceed further? Now, if you look at, if I revisit my question that how do you make this work as an amplifier? Or even before we do that, let us look at another point, which is the trip point, right? So again, visiting the trip point, effect of sizing, right? Effect of device sizing on trip point. So again, qualitatively, how do we arrive at the effect? So this is the characteristics. Suppose you have been given some W by L for PMOS and NMOS. Now, in this, if I say that now I'm going to say increase the NMOS size by 2x. Earlier I have started with WP, WN. Now I want to make 2WN, WP. What should happen to the characteristics? What direction it should move? What should happen? Should it change?
It should move left.
You should go
Towards the left.
Towards the left. Why should it go towards the left?
Because the NMOS pulls down to 0 for a longer time, since it's faster.
Yes, so faster means your WN
Supplies
has been
higher
increased. Yes, so it will basically supply higher current. That means for a lower, as compared to the earlier case, for a lower V in, the NMOS will, start supplying the same current. So earlier, if the NMOS was turning on at a certain point, ultimately it is about the on current, right? So how much current the NMOS is able to sink. So I NMOS. So if the W is doubled for a lower V in value, the NMOS will be sinking the same amount of current as earlier, right? As a result, it will try to pull down the gate voltage, or sorry, the output voltage at an earlier point. So the output voltage will be pulled down at an earlier point. Why? Because the strength of the NMOS has increased. For the same input voltage, that means for the same gate voltage of NMOS, now it is sinking more current. And as a result, it will try to pull down the output more strongly. Remember that this is a transfer characteristics. In order to get the transfer characteristic, what will you do? You will fix the input voltage at different points. So starting from 0, you are going on increasing the input voltage and you are observing the output voltage. So earlier, if you were at the older curve, the output was starting to decrease at a certain point. And that decrease is happening because the NMOS current becoming stronger, right? So as you are going on increasing the gate voltage, NMOS current is becoming stronger. And as a result, you are going to get output voltage which is lower, because eventually in the static condition, what is happening? Both the NMOS and PMOS are going to be equal. How do we get, if you look at the derivation, like rather your Rabe, what kind of equation will you write to obtain the output voltage as a function of input? All you have to do is equate IN equal to IP, because in the static condition, there is no other path for the current to flow, right? Because you're fixing the input DC, output DC will be settled at some point eventually. So all we have to do is equate the IN equal to IP, right? So the NMOS current, PMOS current must be equal for all the input points. Don't confuse it with the transient operation. Transient operation is different. Here it is something like fixing the input gate voltage to different points. Here. You are fixing it here and trying to check what is the output. Next, you are moving to the next higher point, changing the V into the next higher point, fixing it at the DC, and then checking what is the output. So this is something like, checking the output DC level for different input DC level. That's how you obtain the transfer characteristics. So in this case, if I'm looking at the transfer characteristics, how do you obtain the output voltage? You simply do IN is equal to IP. What are the parameters which are going to come in IN equal to IP? 1/2 mu n COX W by L of N and VGS minus VT whole square. So VGS is V in minus VTN. S is 0 whole square. 1 plus lambda N VDS. VDS is V out minus, VS is 0. Right? This is what you're going to get. This should be equal to 1/2 the IP. So if I assume again, the point where the input is just trying to, go up, right? So when the NMOS is just turning on, so at that point, anyway, we have seen that the PMOS going to be in triode region. So for PMOS, we'll have to write the triode region equation ultimately. So it will be mu P COX W by L P, and then you have V in VGS minus VT, VDS times VDS minus VDS square by 2. So now for this, what is VSG? VSG is VDD, right? VSG minus V in, this is your VSG minus mod VTP, right? Times VSD times VSD is V out, VDD minus V out. This is your VSD minus VSD square by 2. So this is the equation that you have. Of course, numerically, it can be solved at different points, and you can analytically, it will be difficult to solve, but numerically, very quickly in the MATLAB, you can write the code different points you can solve. Numerically, if you solve at every point, it will be time taking, but you can write the MATLAB code and obtain the transfer characteristics at different points, assuming that the initial stage, the region 2A, your PMOS is in triode region and NMOS is in saturation region. So ultimately, this is what we are doing. And our quantity of interest is what is happening to V out as we increase the W by L of the NMOS. So from here, definitely if I find out the V out expression, what will happen if W by L of NMOS is increased? So assuming that other parameters are constant, mu P, mu N, COX, etc. is constant, and my output quantity of interest is the two parameters in the bracket, square bracket is also constant, right? V in minus VTN, VD minus V in minus VTN. For that point, it is also constant. So I can, ignore all these other parameters which are constant. Review, draw. So I can ignore all these other parameters which are going to be constant for a particular V in. These parameters are all constant. So assuming that there's some constant factor, I can ignore. So mostly I'll be left with 1 plus lambda N V out and you have, I'm just retaining one factor because that is what is of interest. Others are constant, so I am absorbing it in some constant. And then this side, you have W by L of P, and we have this factor times VD minus V out. And assuming that the V out is still close to VDD, I can ignore the last term, the square term, because V out is at this point still it is close to VDD. So this is going to be small. So I can ignore even this term. So I'm left with this. Is that clear? So this is a simplified expression. You just make some assumptions, and I'm ignoring this term close to 0 and retaining only the constant term W by N, which is of my interest. So this is the overall expression, simplified expression that you get. Can we simplify this further? So going down. So conceptually, what I described, I'm just trying to quantify this. So conceptually, I just mentioned that ultimately, for every point, if you have to find out the output voltage as a function of input voltage, you have to equate the IN equal to IP and derive the function V out as a function of V in. So here I have made some assumption, assuming that the we are somewhere in the middle, in the very beginning of this transition region, in a region 2A. We are talking about that equation. So for the 2A region, this is the equation for, remember that this is for 2A region, as per our earlier discussion. So now going further, we can just simplify this and try to see. So this is W by L N, and this is going to be VDD. So V out, if you see, lambda N plus W by L P upon W by L N, right? This is equal to VDD, the same value, W by L P W by L N minus 1. And then I can divide the whole thing. So if you bring this, over here, you get 1 upon lambda N plus W by L. Again, this the problem is area point of view. I have to shift a little bit. Let me shift. And then again, lambda N is a number which is small, so I can even ignore this lambda N. Remember, lambda 1, what is the value generally you get in your experiments? Have you estimated lambda N, lambda P? What is lambda value? General value of lambda? In your lab experiment, the devices that you characterize, what is the lambda value? Do you remember? Yes, am I still connected?
VA
Hello?
comes around 50 volt, I guess.
So VA comes around 50. So lambda is how much? Like something like 0.01 something, right?
3.02, right?
Yeah. So as compared to W by L, I'm assuming that W by L, W by N are not that far away. Lambda N is definitely much smaller. If you remember, VA is the early voltage that you do in BJT, but in MOSFET also there is a similar part. So you remember that how do you obtain lambda? You have this curve and you extrapolate, and then you get this VA. That VA is much bigger. 1 upon VA, you get the lambda. So that lambda value is going to be around, in the older technologies is going to be 0.01. Newer technologies, because this curve become more steeper, saturation region becomes more steeper. There you may have slightly larger values, 0.03, 0.04 also, but it is a small number. So I can even ignore this. And then I am left with VDD minus. I can just, this one gets over, and then we have W by L N upon W by L P. N and P, right? So this is V out for that region, right? For the 2A region. So definitely, this equation also shows that as we go on increasing the W by L of N, it is going to lower the V out at that point. So is it consistent with what we qualitatively discussed in the beginning? Again, going back, so that's what we discussed, that at this point, if you're looking at the modified curve because of increasing the W by L of N, what is happening? The IN is becoming stronger for a lower value of V in. Conceptually, how will you, even without derivation, conceptually, if you have to explain, how will you explain? So what is happening is that for a lower value of V in, I in is becoming stronger, but I in and IP are same, right? So in order to keep them equal, the output voltage needs to be lower, right? Because the output voltage, if it is lower, then it will equate the IN and IP better, because the VDS factor for the NMOS that will be lower, and for that reason the NMOS current will be getting lower as compared to the earlier case. So what is happening is, for a higher W by L of N, NMOS current is expected to increase, but now NMOS current is equal to PMOS current under all condition. Therefore, in order to counter that, the output voltage must be lower. That's what we can say. So therefore, in simple sense, what we are saying is that pull down strength of NMOS is increasing, or pull down device of the inverter is becoming stronger. As a result, at a lower value of V in, it will start pulling the characteristics down. And that is what is coming in the equation also, that as you go on increasing the NMOS size, the transfer characteristics shifts towards the left. So likewise, if you do it, in the opposite direction, if you are making the PMOS bigger, so suppose I go for 2WP and WN, what should happen? The WP is now bigger. So now if you look at the opposite side, right? So this is moving from the opposite side. WP has become stronger. As a result, now you will need a higher gate voltage to reduce the PMOS current, right? Why the curve goes down? Curve goes down because of reducing PMOS current, right? So now, because the PMOS is doubled, size is double, it is having stronger current, so you will need a further higher gate voltage to reduce the PMOS current to the same value, right? Therefore, you will need a higher gate voltage to turn the PMOS off. Therefore, it is going to shift towards the right. So both these directions should be clear. What is going to happen if I move in one of these two directions? Conceptually, it should be clear. If somebody asks you to drive, quantitatively, I just showed you the method. How do you do that? Taking some valid assumption. Is that clear to all of you? So if you have to get the condition where you have, say, the V out equal to V in curve cutting the midpoint exactly at VDD by 2, then what will you do? And again, I can go back to the same equation. All I have to do is I have to equate IN equal to IP, assuming V out equal to V in equal to VDD by 2. So in that same equation, I can just put V out equal to V in equal to VDD by 2 and equate IN equal to IP and get the condition. If I solve it, it will be something like the W by L and W by L of N and P should be in the ratio of mu N and mu P. So if you just solve this, W by L of N and W by L of P should be approximately in the ratio of mu N, mu P ratio. So this will be something like mu P upon mu N. To equate this current IN equal to IP, add V out equal to V in equal to VDD by 2. That is the condition in which, this is the condition under which you will get the transition point or the trip point of the inverter equal to VDD by 2. Now these are all approximate equations, like all the derivations are done using quadratic equations, which are also approximate in nature. But conceptually, it just tells you that in order to have the trip point close to VDD by 2, I need to have the strengths of the PMOS and NMOS almost equal, right? That means the R on and the R on P and R on N should be almost equal. And that will happen if I, size them in the reverse ratio of their mobility, because ultimately in the current equation, we get that mu P W by L and mu N W by L. And so if we are sizing them in the ratio of their mobility approximately, you will get the strengths to be equal. That means the R1 of N and R1 of P in the central region, the saturation region operation, that will be almost equal. Because saturation region, the equation will be, you just have, both the transistors operating in saturation. You write the saturation region current for IN and IP, equate them with V out equal to V in equal to VD by 2, and approximately this is the relation you get it. So this will be saturation region current for both N and P. Right? So this thing has been done in Rabe also. I hope you have seen that. So in general, this is the thumb rule followed for inverter sizing. So if you have to set the trip point of the inverter close to VDD by 2, we set W by L of N and W by L of P in the reverse ratio of mu N and mu P. So this is for the inverter. What about the other logic gates? So is this point clear for the inverter? Like how are we deriving it? What is the way to get the trip point? Remember, the trip point is the intersection of this curve with V out equal to V in curve, 45-degree curve. This is the V out equal to V in curve. And wherever it is intersecting, it is a trip point. So if we are sizing the NMOS up, then the trip point is going to go down. If you are sizing the PMOS up, the trip point is going to go up. That part conceptually we should know. And then in order to set the trip point equal to VDD by 2, this is the process. V out ID equal to IP equal to IN, saturation region current equation, V out equal to V in equal to VD by 2. So if we look at any other gate, right? So suppose we are looking at any question before we proceed. I am going a bit fast. I am assuming that you have read that Rabe chapter. Any question? I'm not getting any response. I'm hoping that you are understanding things. Yes, hello. Anything not clear? I hope I'm connected. I'm not hearing anything.
Yes, yes, yes.
Is it connected?
So what about some other gates? So we have just discussed inverter trip point, and we are going to discuss some more things. What is this gate? First one. The NOR gate, right? So this is a NOR gate. This is the out. And what is this?
NAND.
NAND gate. So these things you have already done. And using NAND logic, NOR logic, you can construct all kinds of logic gates, all kinds of combinational blocks you can construct using NAND and NOR. Now, in order to, so for inverter, we have seen that if you want to set the trip point close to VDD by 2, we are sizing the PMOS and NMOS in the reverse ratio of their mobility. That means W by L of N, W by L of P is in the reverse ratio of the mobility. Right? So mobility of mu P and mu N. So in different technologies, older technologies, this ratio is almost something like 2 to 2.5 or sometimes 3 also. So approximately in this range, mu P by mu N. Actually, the mu N is greater. So this, I would say 1 by this 1.2.5. So the ratio of W by L N to W by L P will be approximately in this ratio. And it can vary from technology to technology because mu P mu N ratio will change in different technologies, different nodes, 45 nanometer, 65 nanometer, 180 nanometer. So depending on the technology, it may vary slightly, but ballpark number will be something around this. So in your simulation that day, we have seen it was coming almost like 3 times, right? So it was almost as high as 3. So we had to set it to almost 3:1 ratio to get that rise time fall time almost being equal. So so here in this case, so that is another question. Rise time fall time is what we had discussed last time, and how is it related to the trip point? So for the inverter, we have seen that last time we had set the W by L ratios of the PMOS and MOS such that rise time fall times become equal. So how is it related to the trip point concept? So here we are doing trip point, like, okay, make the trip point equal to VDD by 2 almost. So how is it related to the rise time fall time also, as we discussed in the simulation example last time?
Yes, sir, because to keep the trip point at exactly VDD by 2, we are equating the saturation currents and we are keeping them IDSP is equal to IDSN. And to keep the rise time and fall time same, we must keep the turn on resistance of the PMOS side equal to the turn on resistance of the NMOS side. And the turn on resistance has approximately a value of 3 VDD by 4 IDSAT. So that is also to equate them. Also, we need to equate the saturation currents in both cases. So that's equivalent to keeping the trip point at VDD by 2.
Yes, so rise time fall time, as you rightly mentioned, there also we have the charging and discharging time constant for the inverter. The charging time constant depends upon the R on of the PMOS and the load capacitor, and the discharging time constant depends upon R on of the NMOS and the load capacitor. So again, R on of N and R on of P need to be equated in order to have a symmetric rise time and fall time. In terms of trip time, trip point also, if you look at this curve, ultimately the trip point is close to VDD by 2, assuming that the uh, input is having some rise time fall time, finite rise time fall time. Any real input signal will have finite rise time fall time. It will not be exactly, a stepped signal. It will have a finite rise time, finite fall time, or I would say non-zero rise time, non-zero fall time. So now, if the trip point is exactly VDD by 2 or close to VDD by 2, the output will also transition accordingly. It will remain more or less symmetric. If the trip point was, this is, trip point V trip equals to VDD by 2. If the trip point was somewhere else, if the trip point was, say, somewhere else, what will happen to the signal in this case? Suppose the trip point was, close to, say, VDD by, suppose it's higher, so 2 by 3 VDD somewhere here. In this case, the curve will become like this.
Will start falling later.
The trip point is higher, so it will be something like this, and then it will become something like this. So now the trip point is not close to VDD by 2. You can say that if you're having input which is 50% times on, 50% of the time it is off, that is called 50% duty cycle signal. So if I just draw it at a larger scale, assuming that rise time fall time I am representing in a small slope. So if this is the 50% duty cycle signal, which is on of T by 2 times it is on, and T by 2 times it is off. But if this happens, if the rise time, the trip points are not close to VDD by 2, what can happen as we go down the inverter chain? The output signal will become skewed in one direction. It can become, the duty cycle of the signal can change. That is another major problem if you don't have trip point close to VDD by 2. If the trip points are towards the upper value, close to VDD by 2 or lower than VDD by 2, after a particular gate, it will change the ratio of the on time and off time. Right? So you can see earlier the input signal was exactly T by 2 on, T by 2 off, but after exiting, you are seeing that it is squeezed, right? The on duration, off duration are changing. The ratio is changing. So then generally you like to keep this kind of duty, this is called duty cycle concept. Especially it is used for clock signal. So this is something like T on by T period. If T on by T period is exactly 50%, then it is a good clock. if it is getting skewed in one direction after passing through some digital circuits, it is going to distort this duty cycle. Ideally, it is good to have a 50% duty cycle clock. So another implication of trip point is this: if your signal is traveling to gates which are having very skewed trip points, not close to VDD by 2, the signal will get skewed. Therefore, it is important that the gates are sized such that the trip point is remaining close to VDD by 2. Is that clear? So rise time, fall time, that is another thing, that the strength of NMOS and PMOS must be equated. Otherwise, rise time, fall time may also, here I have, the way I have drawn, it may not be exactly symmetrical, because now if your trip point is shifting upward, what will happen? Trip point is shifting upward means which one is stronger? NMOS is stronger or PMOS is stronger? Trip point here, it is shifting. So what is the which one is, like for this case, the way I have shifted the curve from the orange one to the green one, which one has become stronger? PMOS has become stronger or NMOS has become stronger? Just now we discussed, right? From
So
orange curve
PMOS.
to green curve, which one has become stronger?
So PMOS.
PMOS has become stronger because now you are seeing that for earlier, for a lower voltage of input level, the output was going down. Now it is taking a higher input voltage to pull the output down. Therefore, the PMOS has become stronger, or you can say NMOS has become weaker. In that case, if I look at these two, rising and the falling edges, which one will become sharper? Which one will become weaker? Which one will become sharper? Which one will become weaker? The way I have drawn, I have not assumed that effect, but actually what is happening, if your NMOS is becoming weaker, PMOS is becoming stronger, which of these two edges, rising edge will become more sluggish or falling edge will become more sluggish? Quickly, man, after discussing this, it should be fast. I think you people are not getting it. So
if NMOS is getting weaker, then the rising edge, the like when the sorry, the falling edge when the V out falls, that will be affected.
yes,
And if the
so
PMOS
NMOS is
gets
becoming. So who is responsible for the falling edge? NMOS, right? Because NMOS has to pull it down. So if the NMOS is becoming weaker, the falling edge will be more sluggish, right? And rising edge will be faster. So it will further degrade the duty cycle also, right? So this rising edge, falling edge problem, because of the sizing inequality or the turn on, the R on resistance being unequal, if your NMOS is becoming weaker, it will make the falling edge sluggish. If the PMOS is becoming weaker, it will make the rising edge more sluggish. So again, from the point of view of rising edge, rise time, fall time, and from the point of view of duty cycle, it is very important that we try to keep the trip point close to VDD by 2 for all these gates. Remember this, important relation: duty cycle, rise time, fall time, and trip point. So they're all, going to have influence. The trip point, if it is getting higher or lower, it will have effect on the rising time, falling time, and on the duty cycle. And eventually, what is it dependent upon? It is dependent upon the NMOS and PMOS sizes, right? The W by L. Is that clear? Anybody having any problem? This part
Sir,
should
can
be
you
very, very clear.
explain, sir, can you explain after the rise time, fall time? I understood that trip point is shifted, that the duty cycle is reduced. After that, can you explain the rise
So rise time, fall time. So what I said is that from the orange curve to the green curve, what we have done is, first I asked that what is the sizing which is going to lead you from the orange curve to the green curve. So what I said is, now because for it is taking a higher input voltage to turn the output down. Therefore, definitely NMOS has become weaker, PMOS has become stronger. So moving from the orange point to the orange curve to the green curve, NMOS size has increased and PMOS size has reduced, or you can say, sorry, the PMOS size has increased, NMOS size has reduced. The PMOS strength has increased, NMOS strength has reduced. or you can fix one of them. Say the PMOS strength is fixed. So what will be needed to go from orange curve to the green curve? You have to reduce the NMOS strength. Then automatically the trip point will be going up, right? Is this clear?
Yes, sir, that is clear.
Now, if I assume that the NMOS strength has been worsened, it will take longer time to discharge, right? Because discharging process is done by the NMOS. When the input is turning high, the NMOS is responsible for pulling the output down. So
Right.
if the NMOS strength is weaker, it is becoming weaker, the falling edge will become more sluggish. It will take more time to discharge. Is that clear?
Okay. Yes, sir. Yes, sir.
And likewise, if the PMOS strength becoming weaker, then the rising edge will become sluggish, obviously. So
Right.
that will also have effect on rise time, fall time, and will also further degrade the duty cycle, because now you can see that ultimately the turn on time effectively midpoint to midpoint, that will also be further degraded. So therefore, the sizing or making the PMOS device equal in strength to the NMOS device is important for rise time, fall time also, for duty cycle also, so that the trip point being close to VDD by 2 is advantageous for maintaining good rise time, fall time and duty cycle of digital signals. Is this part clear to everyone? So in the simulation, when you do this analysis, by changing the W by L of PMOS and MOS and checking the effect on the output characteristics, transfer characteristics, the transition in the transient simulations, this will become more clear. So these are very important for any digital, as I told you, for any analog circuits also, there will be many digital blocks that you may have to deal with. You may have to integrate some digital units like inverters, gates, etc. So it is important to know the sizing effects. So going further, I am hoping that people are understanding, because I'm not getting much questions. One or two people have asked. Most of those are silent. And I'm also assuming that people have gone through the rabbit chapter. If you had gone through the rabbit chapter, some of these things will be more understandable. Some things I have tried to go fast, assuming that you have gone through the rabbit chapter, because you have got enough time. So if you don't do the reading assignment and if you come without it, you will be definitely at a loss. Because if I'm giving you some reading assignment, you go through it, then the understanding in the lecture will also be slightly better. Otherwise, going through every detail and every derivation will be a little time taking, and that is not needed in order to get you ready for any actual project, etc. That is not needed. That's why parallelly, I'm teaching for 2 hours, but rest of the time you have to invest in reading also, doing simulations also. Then only it will prepare you. You can't rely on the 2-hour lecture. You have to prepare using the reading assignment also and using the simulation also. These two have to go hand in hand. Okay, so I had posed one question that if you have this in NAND gate and NOR gate, then what kind of sizing ratio we will have here? For the inverter, we said that, okay, it is mu p by mu n, so almost around 2 to 3 you may get. So assuming that mu p by mu n is suppose 2, right? For the time being, assume that mu n by mu p is 2, 2 is to 1. So then what will be the ratio for the NOR gate and NAND gate for the PMOS? So rather than redrawing it, I can copy it also. Let me see. Or I can simply redraw it. Doesn't take time. So now for sizing ratio for other gates. So for NMOS, what is happening? Sorry, for NOR gate, what is happening? How do we remember that we have to do R on approximately equal to R on of P approximately equal to R on of N. That's the target. So now, how do we do the R on of N equal to R on of P approximately in this circuit, in the NOR gate? A, B, B.
So like we can do this, that we take the worst case scenarios in each each condition, and then we set the widths such that the net resistance as seen in the NMOS side is equal to the net resistance seen by the PMOS side. And we know that if I scale the width by a factor of alpha, then my resistance will become R by alpha if it was originally R. So, like in this case,
Yes.
the NMOS.
Yes, so that is correct. So here we will look at the worst case scenario. Worst case scenario means for the upper path, charging will anyway happen when both PMOS are on, otherwise it will not charge. So for upper path, there is only one condition, both charging case A equal to B equal to 0. If both of them are 0, then only it will charge, the NOR gate. And in that case, the overall effective W by L of the upper MOSFETs will be what? W by L pull up. I'm calling it pull up. PU equal to pull up because there is a pull up path, and there is a pull down path. These are common terminologies used: pull up and pull down. CMOS, there is a pull up network and the pull down network. In this case, the pull up network is 2 PMOS in series. Pull down network is 2 NMOS in parallel. Now, the W by L effective or the pull up is what? Because now they are coming in series. And for the worst case, that means the only case where it will charge, it is A equal to B equal to 0. So for this case, what is effective W by L of the pull-up? If it is in series, what will happen to the R1? R1 will add up, right? It will be doubled. So because R1 is proportional to W by L, so the W by L effective will be what? W by L, W by L of A and B, assuming they are equal, by 2. Because effectively what is happening, R on is coming in series. R on of A, R on of B series, overall R on is doubled. Therefore, the conductance is half. Conductance is proportional to W by L. Therefore, W by effective is 1 by 2 of A and B each. Is that clear? Yes. Yes, hello?
Yes, sir.
And what about the pull down path? Pull down path was correct condition. So discharging either A equal to 1 or B equal to 1. In that case, is the worst case, right? Because when both are high, then it is going to discharge faster. But the worst case scenario is A or B equal to VDD. If both are high, then it will reach faster. But for the worst case, either A or B, only one of them is high. In that case, it is going to be worst case on conductance, on resistance. So in that case, this worst case on resistance is equal to what? It will be,
R.
I can, here I
that
can
of
say
the-
this is, yes. So this is in the first case, you should distinguish it by calling it P. So P. And second case, in this case, it is simply W by L of A or B, but this is for N, A or B. So this is now effectively the W by L of the pull down network. That is the individual W by L of A equal to W by L of B is the effective pull down resistance for the worst case scenario. Now, if you have to look at the inverter case, effectively for the inverter operation, we were doing it, we were keeping the W by L ratio in the ratio of mu P by mu N. Now, the same thing has to be done, but effective W by L ratio of the pull up path is W by L of half W by L of P, each of the PMOS. And the effective W by L ratio of the pull down is W by L of NMOS. Right? This is the effective W by L ratio because the upper segment, the pull up segment, the effective W by L is half the W by L of 2 PMOS. Yes, coming. And for the pull down network, the effective W by L for the worst case scenario is either A on or B on. So there it is simply W by L of N. Now this we have seen what should be the ratio of this effective W by L of the PMOS and the NMOS network for trip point close to VDD by 2. This ratio should be equal to what? Assuming that mu P mu N ratio is 1 by 2. That's what we have seen.
2:1.
2:1, right? So we want to make the R on of P and R MOS on of N equal. Therefore, this should be in the ratio of mu N by mu P, and that we have assumed to be 1, right? And as a result, we get this ratio of W by L of P by W by L of N approximately equal to 4, right? So in this case, in order to have the trip point close to VDD by 2, and in order to have rise time, fall time almost similar, we will have to size up the PMOS. PMOS has to be sized up. That means it has to be 4 times the W by L of the NMOS. Because we have two NMOSs, sorry, we have two PMOSs coming in series. And worst case scenario, only one NMOS is there in the lower part. So the two PMOS need to be equated to the single NMOS. Earlier it was one PMOS, one NMOS. Then we were requiring 2 times the the PMOS size was twice that of NMOS. Now it is two PMOS in series competing with one NMOS in the pull down. Remember one NMOS because of the worst case scenario. So two PMOS in series competing with one NMOS in the pull down definitely will require double the width. Therefore, in this case, the W by L of PMOS is going to be 4 times W by L of NMOS. Is that clear? And the second
Yes,
scenario is the NAND gate. So just the opposite, right? So for the NAND gate, we have two PMOSs in parallel in the upper segment, two NMOSs in parallel, series in the lower segment. So you have A, B, B over here, and you have the output over here. So now in this case, if you have to look at the worst case pull up. So pull up network, worst case scenario, only one of them will be on, right? Either A or B on. That will be the worst case pull up. That means A equal to 0, A equal to 0, or B equal to 0. This is the worst case pull up because only one of the devices are pulling up. So in this case, the effective W by L for the pull up will be simply W by L of P. Effective W by L pull up effective will be W by L of P, because worst case scenario, only one of them will be on and charging the output. As a result, effective W by L of pull up network is simply W by LP. But for the pull down network, I need A equal to B equal to VDD. Both has to be on so that output can discharge. And therefore, for the pull down effective W by L of N, I can call it pull down effective will be what? Because not there are two in series, and therefore this will be W by L of N half, because the conductance is going to be half. There are two are coming in series to discharge the output. Now, therefore, you are going to get this, effective ratio of pull up and pull down network. The W by L pull up by W by L pull down effective is 2 times W by L P by W by L N. And this ratio should be equal to what? For rise time, fall time, remember, we are just doing effective W by, because this is proportional to R pull up. Sorry, just the opposite. So conductance G pull up. Let me delete this. So this is proportional to G pull up and G pull down. G means conductance. So we have to equate them. So now in this case, this ratio has to be what? Earlier we have seen inverter case, it was again, mu N by mu P. Again, this is 2:1. Therefore, in this case, it will be approximately 1. So for the NAND gate, the PMOS size and NMOS size will be approximately equal to 1. Or basically the ratio will be approximately equal to 1. All the sizes will be same. If this is W by L, this is also W by L. Is that clear? Because in this case, the NMOS is anyway in series. Worst case scenario, two NMOSs are coming in series. Conductance is half. Therefore, effectively, the W by L effective of the NMOS network or the pull down network is W by 2. And whereas for the worst case scenario, pull up network W by L is given by only one of A or B. and that will be W. So therefore, W and W by 2. And therefore, now the setting is that we need the pull up and pull down conductances to be equated to the, we need them to be equal, and that needs the effective W by L ratio to be equal to mu n by mu p. So this resizing concept you should remember that what is happening for an inverter, what is happening for a NAND gate, what is happening for a NOR gate, right? Any question before we proceed further? Any question before we proceed further? I hope, in case you feel that something is going very fast and you're not able to understand, feel free to interrupt. And so using inverter or CMOS inverter as an amplifier. So this is something I discussed in the beginning, that if I bias the inverter in the high gain region, in this region, then the slope del V out by del V in is maximum. And as a result, you will get amplifier operation. And assuming that, it is sized such that this is close to VDD by 2, VDD by 2. V out equal to V wherever it intersects. And suppose we have sized it such that V out equal to V in point is cutting it at, this VDD by 2 point. So now in this case, how do we use it as an amplifier? So what do we need to do to make it operate as an amplifier? How do you bias it? Given this inverter, how do you make it work like an amplifier? Anybody? If you have seen some of my lectures, earlier recorded lectures, maybe I have discussed it somewhere. But how will you make it work as an amplifier?
We'll find
Connect
these
V in and V out.
Connect?
V in and
Sorry?
V out.
Connect
V
V in
in
and V
and
out,
V
then will work as an amplifier. So connect this, it will work as an amplifier.
Oh,
Yes. What else? What can be done?
so connect the resistance between V in and V out.
Okay. So what will this resistance do?
Feedback.
Feedback is fine, but what is this resistance going to do? Like, why is it working like an amplifier? How is it going to help it in working like an amplifier? Yes, anybody? Quickly. How is it going to work like an amplifier? Suppose you have a capacitively coupled input, right? You are CC applying a signal, V in AC signal. Now, can you tell how is it going to work like an amplifier? In this case, in the previous case, what was the problem? In the previous case, without the R, what is the alternative? The alternative is that, okay, you put a AC source in series with a DC source. You put this DC source somewhere close to VDD by 2, and you have VAC. And then if you look at only the DC point, if it is close to VDD by 2, probably it will bias it close to the high gain region, and then you apply the AC signal. Is this clear? The first case, this thing should work. What is the problem of this? What is the problem? Any problem that you see in the second, whatever I drew just now? Yes.
So drain is floating.
Drain is floating. That's not a problem, right? You whatever you can have a fee. Effectively, you know that output is always having a parasitic capacitor. So whether I put a CL or not doesn't matter. It will at least have the parasitic capacitor. Yes. Any problem with this approach? Yes, quickly, anybody? So all of us, I think we have discussed this concept of variation, right? So from device to device, the VT of NMOS, PMOS, etc. will vary, right? And as a result, uh, you may not be having the same, exactly same VT, and therefore for different inverter, different amplifier, the trip point will vary, right? For the same W by L ratio also, if I include the VT variation in the current equation that we just looked at, in the present scenario, we have assumed some ideal conditions. VT is same for both of them. Mod VTN are same, and they are fixed values. But in general, those values will vary significantly. So if the VT is varying, the threshold voltage from device to device is varying, lambda values are varying. Even if you set the device ratio to be, equal to the equation value, equal to the mu and mu ratio, if the VT changes, then the trip point will change. And therefore, your gain, you may have assumed that you are biasing it to VD by 2, therefore, you should get very high gain region. But if suppose the VT of NMOS is becoming slightly higher than PMOS, what will happen to this curve? This is what you simulated. But after fabrication of the circuit, the VT of the NMOS came higher than expected. What will happen to these characteristics? Yes, anyone? Same question, whatever we discussed just now, the same question. Only thing is I have replaced W by L with VT. So what I'm saying is you have done the simulation, you have sized the PMOS and MOS so that VT by 2 is the trip point, and that requires mu P by mu1 ratio equal to something like 2. W by L ratio is equal to the mu P mu1 ratio, and MOS PMOS ratio is going to be mu P by mu1 ratio. So that is approximately 1:2, assume. Now, but after fabrication, what happened? You saw that the NMOS threshold voltage was slightly higher than expected. What should happen to the curve?
Will
shift to
require
the
more
right,
gain.
Shift towards the right.
The top part will shift to the right, while the lower part remains same.
Yes, shift towards right, because now you're going to require higher voltage to turn on the PMOS. Higher input voltage, turn on the PMOS and discharge the output. Therefore, the curve will shift towards right. Now you had, assumed that you're biasing it in the high gain region, but it ended up here, which is a very, poor gain as compared to the ideal gain. Therefore, it is not going to be suitable. It is not going to be robust. If you design 10 such amplifiers, amplifier 1 will give you a different gain, amplifier 2 will give you a different gain. All of them will give you different gain depending upon the small variations in the VT. Right? This concept is clear to everyone. This is very important. So small changes in VT will lead you to different points in the transfer characteristics. It will shift the transfer characteristics. So you will not be ideally at the midpoint, depending upon which VT is higher, PMOS is slightly higher or NMOS is slightly higher. You may shift towards low gain region. Is this point clear to everyone?
Yes.
So then what is the benefit of the first, like when we put a R, suppose the R value is large, in the first case, this problem is going to come here. But in this case, when you put the R and suppose the signal is AC coupled, there is no DC current, right? So in this case, there is no DC current into the gates. So IG is 0 for both PMOS and NMOS, right? As a result, DC point of view, it is forcing V out equal to V in, automatically ensuring that V out is equal to V in. Because DC point of view, that is what is going to happen. And therefore, you are automatically landing onto that point where the transfer characteristics is crossing that, V out equal to V in point. Of course, now that V out equal to V in point, if the sizing is varying too much, there also you may have variation, but at least it is ensuring that you are setting it such that V out is equal to V in, and you are going to at least land up in that slope region, somewhere in this. Of course, your sizing is too bad and your slope is cutting somewhere here, then you can't say that. That is an extreme variation. But nominally, at least you will end up, having, if there is a variation in the slope, still you will have some range. This is going to be more tolerant towards the VT variation. Even if the VT of NMOS is actually varying, at least we are fixing the V out equal to V in. So the possibility of, staying in the high gain region will be more. And then what should be the value of R? If your R is infinity, close to very high value, what will happen? Ideally, DC point of view, still, as long as R is non-zero, R is finite, you still have DC V out equal to V in. R is very large, but finite, suppose. So V out is equal to V in. And in the small signal analysis, you can ignore R. Therefore, the gain will be what? Gain in this case, if I assume that R is very high, what will be the gain? How will you calculate the gain of this circuit? Assuming that R is very high. The small signal gain.
You use a superposition that, like, first the current,
Superposition,
the
right?
signal goes.
So you just assume, two different devices, NMOS, PMOS. In first case, you apply V in equal to 0, V in here. Assume that the gate of the NMOS is at the DC voltage. AC point of view, it will be 0. This is your, VAC equal to 0. And you apply a V in at the gate of the PMOS. So, and second case, you apply the AC signal at the NMOS gate, and the AC signal at the gate of PMOS will be 0. Although they are tied together, but in order to get the total gain, I can just use superposition. First, apply the small signal at the gate of PMOS. Assume that the NMOS gate is at DC. Therefore, AC point of view, it will be 0. And the other case, you just reverse. So it will be A1 plus A2. A1, the case where you apply the signal at the gate of PMOS, it will be minus GMP times what?
R out N.
Sorry?
R out of N.
R out of N.
Yes.
Anybody else?
R out of P.
Common source amplifier with active load, what is the gain? This is something like a common source amplifier with
Parallel to
R out P parallel R out N. R out P parallel R out.
yes. So this thing should be clear. This will be R out N parallel R out P, right? This part you should be clear, because common source amplifier, how will you draw the small signal model of this? Ultimately, you will get R out RO P between drain and the AC ground. This is AC ground, right? So this is VDD, but AC ground. And likewise, you will get RON, which is also between output and AC ground. So ROP and RON will come in parallel, right? Because both of them are between output and AC grounds. Therefore, it will be minus GMP times R out parallel R, R out N, or rather RON parallel ROP. A2 is also minus GMN, same thing, R out N parallel R out P. Therefore, it is going to be superposition of these two in this region. Assuming that both are in saturation, I can apply this equation. Is that clear? But in case R becomes finite, what will happen? Other extreme, when R is becoming almost close to 0, you shorted it, right? The very first case, somebody said that will short output and output. In that case, what will be the gain? If you short R, the R is 0. What will be the gain?
Gain will always be 1. Always be 1.
Gain equal to 1. There is no gain. Gain is unity. So, this is the maximum magnitude of the gain that you can get. minimum magnitude will be equal to unity when R is shorted. So definitely, we would like the R to be high. We would not like the R to be close to 0. Otherwise, the gain will be diminished. So how high we can go in terms of R? Who will decide that? Here, it seems like keeping R very high is okay. But what is that very high? Is it 10 mega ohm? Is it 1 mega ohm? Is it 100 kilo ohm? How will we decide that? Who will decide that? What is the design matrix that will decide? Let us decide what is the effect of R. Like how high should the R be?
Capacitors,
So-
the capacitors.
Okay, so
which
what will that capacitor do? How will they decide what will happen? Like with the capacitor, what is happening?
Sir, it will determine the bandwidth up to which it will work, basically.
So what will happen to the bandwidth if the R is increased?
Then the RC value will increase, so the bandwidth will degrade.
Degrade means in what manner? Will it become more low pass, more high pass? What will happen? The C is forming what kind of filter with the R?
It will become more high pass.
So if the R is
Not
reduced, what will happen if you go on reducing the R, the RC pole, because this is something like a high pass filter, right? So what will happen? The RC becomes, if R is small, RC becomes smaller. 1 upon RC will become higher. So the high pass pole will shift towards higher frequency. So the larger R may be good for, if your R is large, the RC time constant for the high pass will become large. As a result, 1 upon RC will become short, shift towards lower value. Therefore, larger R will give you, if you look at the bandwidth, this part, this will become further closer to the origin if your R is larger. What about the high pass? So if you look at this other pole, high pass pole, what will happen to that?
It will move closer.
Sorry?
So that will also move higher, right? Because of the capacitances, the drain body capacitances of the NMOS.
Yeah,
and the
because if the
PMOS.
R is very large, effectively it will not, you can ignore the R if your R is much larger than RO. Miller effect, you can apply the Miller effect and you can break the R, put the, effective R here, R effective. And then you can see that if the R is very high, definitely it will play lesser role. If the R is lower and lower, it will play more role. So lower R will definitely diminish the gain. That's what we see. Eventually, the R is sent to 0, it will reduce the gain to unity. So effective R, right? If your effective R over here is getting reduced, you will have lower and lower gain. I remember that Miller effect will be applicable if you have large gain. If the gain is becoming smaller and smaller, that that approximation will not be exactly valid. So in this case, at least the gain point of view, we know that lower R will give you poorer gain. Bandwidth point of view, if you are putting, say, lower R, a higher R is giving you basically a broader bandwidth. If your R is very high, it becomes the R effective becomes, you can ignore it as compared to the ROP of the PMOS and RON of the NMOS, and therefore the bandwidth will become, it will be the worst case bandwidth. If your R is lower, then that will lower the gain, but it will slightly improve the bandwidth. So the gain bandwidth product, anyway, we have a reverse relationship. If your R effective is lower, if you are using lower R, so that the R effective is lower, gain will be reduced, but bandwidth will be improved because at the output node, the effective R is reducing, that is becoming comparable to the ROP, RON. The effective output impedance is reducing. As a result, the upper cutoff will improve while the gain will drop. Is that clear? Is that clear? Any problem with this? In general, the on-chip circuits do not use very large coupling capacitors. Generally, even if you use coupling capacitors in on-chip circuits, they will be very small. In your breadboard circuits, we use very large coupling capacitors, microfarad, several, you can also use several tens of microfarad, doesn't matter. But on-chip circuit, the on-chip capacitors that you can use in an integrated circuit, that is generally much smaller. And that is because the capacitor takes a lot of area. How do you form a capacitor? Just like, the normal case, when you have to design a capacitor in a chip, you have to basically use two metal layers. In between, there has to be a silicon oxide, and then you form the capacitor. So larger is the capacitor, larger is the area of that capacitor on the chip. And chip area is very costly. We cannot have very large capacitor on the chip. If you have, say, 1 millimeter square chip area, suppose you design a chip 1 millimeter square, 1 millimeter by 1 millimeter. Even if you fill this entire 1 millimeter square chip with only capacitor, the maximum value you can get will be maybe few nanofarad. So few nanofarad. You can understand that overall the coupling capacitors, etc., that we can use in circuits on chip will be much smaller. So they will be of the order of picofarad or femtofarad region, fraction of picofarad. So picofarad or femtofarad region. So generally we may have 50 femtofarad, 100 femtofarad, 1 picofarad, around that kind of value. So on-chip capacitor values are limited to these values. We can't use very big capacitors. So in some applications where big capacitors on chip are required, you may approach at max, say, few hundred picofarad, but more than that is very difficult on chip. That constraint we should have in mind. And in this case, like the breadboard circuits, we use big coupling caps. That is not possible on the chip. It will be either using very small values. Accordingly, you will have to figure out what is the bandwidth, because if the C value is much reduced, you are again increasing the this particular frequency towards higher value. That is not advantageous. So those constraints we will see as we design circuits with RNC, how the limited capacitor plays a role, that we will see. But in case the previous circuit is directly coupled to this node, that means if we do not have AC coupling, then this R will also play effect in loading, right? It will load the previous circuit. So if you don't have CC at all, directly the previous stage is driving it, having a larger R will be beneficial because it will not have any significant loading effect. Because almost like open circuit, right? Whereas a smaller R will have some loading effect. It will load the previous stage. It will have an effective R. So I will give you some assignments through which you will be able to appreciate these points. Any point, any question before we proceed further? So I think we had enough for today. I will, send some assignment for all of you. Any question before we conclude?
Sir, one question I had that was regarding one thing that which I read in the Rabbi book, that is about the velocity saturation. So, say in the Rabbi book, they had mentioned that the small channel devices, like the one which is using around 45 nanometer, so they said that in that there is something called velocity saturation, in which if my the gate voltage, if I have a very high gate voltage, then
Yes.
saturation may occur at lower values of Vn, which is less than VGS minus VTH. The problem is that I tried in LT Spice with 45 nanometer device and 180 nanometer device, but it seems like the 45 nanometer device is actually getting saturated at a higher voltage than the 180 nanometer device, and is also consuming slightly higher current. Sir, that was what I wanted to ask, that why is that happening?
So again, VDSAT, there are a lot of device parameters, right? So your threshold voltage is another parameter, lambda is another parameter. So the threshold voltage also reduces every channel, every node as we go from higher nodes towards lower nodes, the threshold voltage keeps on reducing. And if your VDD is you are not reducing, suppose you're using the same VDD for both of them, the current will effectively increase. Right? So VT has reduced, but VDD you are using is same. In that case, the current will increase. So generally, as we scale down from 180 nanometer to 45 nanometer, the supply voltage also supposed to scale down. For 180 nanometer, the supply voltage is 1.8 volt. For 45 nanometer, it will be either 1.2 volt or 1 volt. So if you reduce the VDD, then you will see the effect.
Yes, sir.
Is that clear?
Yes, sir.
Those things, I mean, right now I have not covered the MOSFET scaling concept. So there will be one session at least on, maybe in the next session, I can describe the MOSFET scaling, what happens to VT, what happens to VDD, what happens to switching speed, what happens to power consumption as we scale down the MOSFET. So that's entire scaling phenomena. I think I might have recorded it somewhere also. If I find it, I will share. Otherwise, I will cover in the session. Any other question? Scaling effect of MOSFET is very important.
How
Yes, hello.
I couldn't understand how the higher frequency of the bandwidth is getting is changing with the value of R.
So if you look at the overall R, right? So again here, you will ultimately break it using Miller effect into an R effective here, right? So you will get some R effective. So ultimately at this node, you are having some C effective also because of parasitic capacitor. But if you look at the CC and R, they are forming what kind of filter? It is a high pass filter, right?
Yes, sir.
So if your R value is reduced, what will it do? It will push the RC time constant is reducing, 1 upon RC is increasing. And for this corner frequency, the high pass corner frequency, if your R is reduced, it will shift towards higher frequency, which is not desirable, right? Because it will not be able to operate the signal at lower frequency. Is that clear?
Yes, sir.
Any other question? Another thing that we should look at is the gain. So since in this expression we are getting the gain equal to GM, magnitude of the gain is GM P plus GM N times RO parallel, RON parallel, ROP. This is the gain. So if you have to get a really good gain from the circuit, these are the parameters, assuming that R is high. These are the parameters. So what will you need to do for having larger gain? How will you size the device? How the device sizing will influence the gain? Yes, anyone?
Sir, we need to have higher values of GM, so that will require my high values of W by L ratio. But the current should be low because the GM is proportional to the root of current, whereas the R on parallel RON parallel ROP is proportional to inverse proportional to current. So the current should be low while the W by L ratio should be high to keep a high gain.
So root under ID and root under W by L of P plus root under W by L of N, right? Times 1 upon lambda ID, right? So 1 upon lambda ID. Again, you can, just using lambda as a common thing, but you have lambda N parallel lambda ROP, you can combine. Effectively, this is the equation. So definitely we are getting 1 upon root ID and we are getting root under W by L and root under W by P in the numerator. So what does that tell us? That if you increase the root under W by L, that means W by L of N and P if you increase, and you have 1 upon lambda ID. What does it lambda depend upon? How does it depend upon L?
Inversely proportional to the length.
Inversely proportional to the length, right? So the lambda can be, assumed equal to, say, some constant lambda naught times L. So effectively, I can of course combine this in a, because this is RON parallel ROP. So each of them will be RON inverse of RON 1 upon RON plus ROP. And each of them will give you lambda naught times L. So effectively, I would like to basically have larger W by L and at the same time also larger L, because that larger L will give you larger RO and larger W by L will give you larger GM. Therefore, you will get, if you are increasing, because here there is no bias current. The bias current is also dependent upon W by L. Now this root under ID that we are putting here, that is in itself dependent upon W by L, right? So I can again, let me write it afresh. So here, first thing is you have the GM dependent upon root under ID, and the two W by L are coming. And then you have the RON parallel ROP. So which is something like 1 upon RON plus 1 upon ROP inverse. And each of this, if I look at upon this thing, if I just look at the RON parallel ROP, this is 1 upon lambda ID. So this is lambda N ID plus lambda P ID inverse. And then lambda N and lambda P, they are also inversely proportional to the L. So this will be ID upon some lambda naught times Ln plus ID upon some lambda. You can say lambda naught 1 because they may not be exactly same, lambda naught 2 LP. Remember why your lambda increases with channel length, because if you have longer channel length, the saturation, the pinch off is stronger, your slope becomes flatter. So shorter channel length, generally your slope becomes more. Larger channel length, the delta L by L factor that you get, the fractional change in the length that you get is lesser. That might have, you have seen in the MOSFET current equation derivation. So the fractional change delta L by L becomes smaller and smaller if your length is bigger. Delta L is dependent upon the applied voltage, bias current, the doping concentration, etc. Delta L is dependent upon the how much depletion region you are creating over here, and that is dependent upon the bias voltage and the doping concentration on the NP side and NN side. But if your total L is large, then the fractional change in the length delta L by L is small. Therefore, the overall RO becomes larger. Effective channel length resistance becomes larger if your channel length is bigger. So I'm assuming this part we have seen in the derivation of the lambda and the derivation of the MOSFET current characteristics. If I assume that, then this is the condition, and then I can just bring it here. You will get ID out here, and then you will get the 1 upon lambda naught. These are just constant ln plus 1 upon lambda naught 2 LP. So 1 upon root ID we are getting. Definitely reducing the ID will improve the gain. And second is, if you look at the ln and LP. So if I look at this, if you increase the ln and LP, as well as if you increase W of L and W of P, you will get bigger gain, right? So that means here W has to be increased, W has to be increased. Here ln and LP are under root, here it is outside root. Increasing the ln LP will also improve the gain. So ID, now ID, if I just, because here there is no bias current, if I just break the ID into the W by L dependency, ultimately this also depends upon W by L. So this is something like, W by L, P and W by L N. So if I take just one of them, so it is also having W by L, the M dependency. So in this case, now if I assume the dependency of L factor here, if I assume that roughly this 1 upon root L is getting cancelled with the upper one, you are left with the 1 upon lambda naught L N and 1 upon lambda LP. Therefore, the increasing the channel length in this case will help you in getting bigger gain, because it reduces the current and it basically increases the RO of the devices, and reducing current and increasing RO will help you in getting better gain. So this part you can check, what is happening. So again, exact derivation, taking all the terms of NMOS, PMOS will lead to a more extensive derivation. But the trend is here that if you want bigger gain, you can try to increase the length. And W point of view, because the GM ultimately, if you derive it exactly, you will have some, the residue W will be coming in the numerator. So it has some effect on the GM. So larger W and larger L both will help in getting you improved gain in this circuit. So this part, I will give you some assignment and you can see the effect of W and L on the, the MOSFET overall small signal gain on this circuit. If you have a general amplifier structure like differential amplifier, there anyway you have bias current, which is independent. In this case, bias current is dependent upon W by L. So that if you are increasing the L, in any way the bias current is going down, RO is going up. And effectively, if you look at the individual gains, so from each side, if you look at the individual gain, for the PMOS side, for example, GMP times RO. So if you want to have more clarity, you can just look at the individual sides. So GMP will be dependent upon, again, root under W by L and ID, and RO2, ROut and RO, ROP and RON will also depend upon 1 upon lambda ID. So individual gains also you can look at it. It will also follow the same trend, right? So in this case, if you increase the L, gain will be better. But what is the cost at which it will come? Larger L means what? Larger L means what?
Over switching.
Sorry? Larger L, we are going for larger RO, right? Larger L is giving us larger RO. But what is the effect of larger RO?
Switching would be slower.
Sorry? Once again, anybody? Like, what is the effect of larger RO?
Switching would be slower.
Slower. Slower means why it will be slower?
Because the capacitance which is seen and the RC product will be higher, so it will be slower.
Yes. So bandwidth of the circuit depends upon the RO, right? The RO is larger. Your RO is larger. That means you are going to get lower bandwidth. Your speed of the circuit will become slower and slower. So this also should be clear. So any question on this before we proceed further? We can close for today, and I will give you some simulation assignments to be carried out. But any question? Bandwidth point of view, there is always a trade-off between gain and bandwidth. Any amplifier if you take, if you try to improve the gain, as in this case, you are seeing that if you increase the L, it will improve the gain, but it will come at the cost of lower bandwidth. So RC time constant at the output will be bigger, the circuit will become slower, bandwidth will become poorer. We have not considered the noise analysis. I think you have also covered some lectures, the recorded lectures on noise analysis. All of you have seen noise analysis lectures. Hello. In one of the recordings, there were some basics of noise analysis discussed, like the device noise model and the small signal noise analysis.
Yes, sir.
So likewise, here also we can do the similar noise analysis. Ultimately, it will be something similar to the common source amplifier with active load. If we assume that the R is large, so that part we can look at in the next session, where different amplifiers noise analysis can be done. So any question before we conclude? I will give you assignments on the basis of this amplifier and also the inverter, whatever we have discussed, rise time, fall time, and the sizing ratios, the duty cycle effect, all those things, once you simulate, it will become more clear. Likewise, the amplifier operation for capacitive coupling case, without capacitive coupling case, and how to, how does the sizing affect the gain, all those things we will try to look at. There are alternate versions of this also. Means I have seen people controlling the current of this circuit as well. So one way to make the current independent of this is to use a bias current. So along with this, you can if you put a bias current, that may be, for a differential circuit, it may be helpful. Single unit circuit, putting a bias current is not going to be feasible, but differential version of this, you can put a bias. That part probably we can discuss next time. In this case, we are having a simple inverter, just with the help of that you are getting it operated as an amplifier. And the gain bandwidth trade-off, just like we are seeing here, it is available. The same thing is happening in other amplifier topologies also. Any question before we conclude? I will print this and I will send it to you. I will again check for, there are a couple of more things that I can quickly cover because we have considered these transfer characteristics and we have also discussed about variation. So a very quick addition to this, effect of variation on transfer characteristics. Or let us keep it for the next, it will become too much. So variation, the corner effect that we will discuss tomorrow. Any question before we conclude? Nobody has any question?
No.
Okay, so I will post the whatever the notes and some assignment steps in the group. Try to complete it by tomorrow. So remember that whatever additional reading is being given and the simulation examples that are being given, you need to follow that and complete that before the next lecture, so that discussions are more clear and also you can ask more questions. If you don't do those things, if you are not coming with the simulations done and your reading assignment is done, I am assuming that based on those reading assignments, some parts you have covered. Therefore, I have gone through some parts faster, like this VTC discussion, some parts even a little fast. But if you have not read that Rebbe chapter, it may be slightly difficult to catch faster. So next time onwards, if you have those people who have not covered Rebbe chapter, please be sure that whatever is being given as a reading assignment before the next lecture, you finish it off. And completing one chapter, it should not be taking so much time, especially after you have covered the analog digital circuits courses. It should not take much time. Okay, so let us conclude.